Today we would like to present to you about role of transition metals in coordination compound, the case of hemoglobin. In this section, we aim to understand what transition metals are. D block elements will partially fill d orbitals, and what coordination compounds are, where a metal ion binds to molecule or ion called ligands. We will look at how metal ligands bond form, the role of d orbitals, and how this interaction give a rise to the structures and properties of coordination complex. Hemoglobin is an example of a biological coordination compound where an ions is coordinated to a porphyrin ring and protein ligands, enabling oxygen binding and transport in the body. Finally, we will explore everyday application of transition metal from industrial catalysts, pigments, and electronics to essential role in a biological system.
For the introduction is transition metal is an element where the atom has a partially filled d orbital, which in other hand can give a rise to cation with an incomplete d subshell. Transition metal also an element in the middle of the periodic table such as iron, copper, and nickel that can form ions with a different charges and have a unique properties like conductivity and magnetism. Coordination compound are the molecules that contain one or more metal centers that bound to ligands. Ligands can be atoms, ion, or molecule that transfer electrons to the metal. These compounds can be natural or charged. Plus, when the compound is charged, neighboring counter-ion will help to stabilize the complex. Why both of these are so important in chemistry? It is because from the transition metal, we can make a hemoglobin to do their job in the body as a red blood cell. Meanwhile, coordination compound will help us to exhibit different properties and use in synthesized organic molecules.
Transition metal are d blocks elements that can form ions with partially filled d orbitals. This electronic structure gives them unique chemical and photochemical properties. One important property is variable oxidation state. Transition metal can exist in more than one oxidation state, which enable redox reaction and photo-induced processes. For example, iron commonly exists as iron 2+ and iron 3+, while copper can exist as copper+ and copper 2+. Another key property is the formation of complexes. Transition metal readily form coordination complexes with ligands. This complex can be designed to control light absorption and biological activity, such as in phototherapy anti-cancer application using copper 2 or iron 2 ligands complexes. Hemoglobin is a metalloprotein made of 4 protein subunits, each containing a heme group with an ion 2 ion at its center. These ion form a coordination complex within a porphyrin ring and can bind small molecules. Its main chemical function is to bind oxygen reversibly. Hemoglobin picks up oxygen where oxygen levels are high and releases it where oxygen levels are low. Hemoglobin also exhibits allostery and cooperativities. When one heme binds oxygen, the protein changes shape, increasing the oxygen infinity of the remaining hemes. This allows hemoglobin to transport oxygen efficiently under changing conditions.
So, for bonding in hemoglobin, based on valence bond theory hemoglobin is a really interesting protein because it has iron 2+ ion, which is Fe2+, right at its center. And around this ion, the nitrogen atoms in the heme group act like a little helpers, donating their electrons to form coordinate bonds and using for valence bond theory, we can see that these bonds happen because the orbitals of iron and nitrogen overlap perfectly, and it's creating a stable octahedral structure. And this clever arrangement is what allows oxygen to stick to the iron in our lungs and then release it in our tissues whenever our body needs it. So basically, the way iron and nitrogen bond is what makes the hemoglobin so amazing at carrying oxygen all over the body.
Next is hemoglobin as coordination compound. First, central metal ion. Each hemoglobin molecule has 4 heme groups. In each heme groups, the central metal ion is iron 2 Fe2+. Second, coordination bonding. The bonds between Fe2+ and the nitrogen atoms or oxygen are coordinate covalent bonds, and ligands donate lone pair electrons to the empty orbitals of Fe2+. Third, ligands. The Fe2+ ion is coordinated by 4 nitrogen atoms from a porphyrin ring, 1 nitrogen atom from a histidine residue of the globin protein, 1 oxygen molecule binds reversibly as the 6th ligand. Lastly, geometry. This gives iron a coordination number of 6, forming an octahedral coordination geometry.
So, for this slide, I will explain the importance and application of coordination compounds in the human body using hemoglobin. Like I said earlier, hemoglobin is a coordination compound containing an iron 2+ ion at the center of a heme complex. The iron forms coordinate covalent bonds with ligands and allowing oxygen molecules to bind reversibly. In the lungs, where oxygen concentration is high, hemoglobin forms oxyhemoglobin, and when it reaches the body tissues with lower oxygen concentration, the oxygen is released. And this reversible coordination bonding allows efficient oxygen transport in the body, and therefore hemoglobin is an important example of bioinorganic chemistry and shows the real-life application of coordination compounds.
In conclusion, transition metals are important in inorganic chemistry because of their ability to form coordination compounds. These compounds are formed when a central metal ion bonds with surrounding ligands through coordinate covalent bonds. This concept is clearly demonstrated in hemoglobin, where iron acts as the central metal ion and binds to ligands and oxygens. This application shows that coordination chemistry is not only theoretical but also plays an important role in biological systems and daily life.
This is all reference that we've been used for our video presentation.